my screen.
Okay.
Okay. Okay. I need
Sorry,
to put...
I want to make a statement. Sorry, Professor Marcel Topor.
Yes.
About the paper of our friend Tihomir. It's
Okay.
a statement, not a question.
Just a moment. I will stop this. Okay.
Yes.
I saw that between the option for artificial intelligence is one very interesting, like make a new culinary recipe. I hope that the next conference will benefit from this option of artificial intelligence. Thank you. Sorry.
Oh, thank you.
Yeah. Okay. Let me start the presentation.
Okay.
If there is nothing else.
Yes.
Okay.
Okay. You are in presentation, we see.
Okay. The paper I will present you today, it is entitled The Use of Geothermal Waters in Energy, Residential and Agricultural Fields. The paper authors are Sorin Ioan Deaconu, Marcel Topor, Bu Fei Fei, and Alexander Mihai Blaj. It is a joint paper with our colleagues from Nanjing University of Aeronautics and Astronautics and Al Salah University College of Engineering, United Emirates of Arabia. Now, the title of the paper introduces us in a problem regarding the use of very clean green energy, the geothermal energy. The geothermal energy, it is an energy which is stored in the ground. Basically, the Earth itself is a giant thermal battery which is providing us with the heat from the beginning. Now, why do we need to orient ourselves in exploring this type of energy beside the solar and the wind energy? Because due to the social development of society, we will require many resources in order to heat and to power all the technical civilization we have at this moment. Now, the geothermal energy, it is a renewable energy. It is used in several applications in order to reduce carbon emissions, in order to lower the energy costs. The source of this energy comes from the ground of the Earth. Basically, the Earth itself, it is a extraordinary source energy capable of sending toward the surface about 47 terawatts of energy. Now, this energy comes from two main sources in equal amounts. One part of this energy comes from the radiogenic heat produced by the radioactive decay of isotopes in the mantle and the crust of the Earth. As you see in this picture, the shares of energy produced is almost equal between the different layers. Now, and the second source is the primordial heat left over the formation of Earth. From the point of view of availability, the temperature gradient, which indicates the distribution of temperature between the different layers of the Earth, varies depending on the depth. For example, on some areas at a depth of 500 meters, we may have 27.5 degrees constant temperature. Below the 1000 meters, we may see an increase of the temperature, and the reachable point using conventional drilling equipment might be 5000 meters, which is capable of providing generally with a temperature of 140 degrees. Now, this kind of temperature are very useful in applications for heating and also in electric energy production. In Romania, as you may see in this slide, it is a really interesting situation. The distribution of the geothermal energy was investigated long time ago, and basically we have several areas which are indicating the good access to this geothermal energy. One particular region, it is the western side of Romania, basically Oradea up to Arad and Timișoara. This region of the national territory actually takes part of a rather large area situated in the Pannonic Basin. Now, if you look at this map, we see also that even Serbia has a good access to the geothermal region, the geothermal resource, and this indicates a good opportunity in order to explore the geothermal energy. Now, in this particular area, it have been developed several applications, and we are considering in this paper a solution located in this in this part, Oradea, in order to investigate the feasibility. It is a pre-study in order to evaluate the geothermal potential and economical return from this technology. Now, these regions, geothermal regions, are classified in two types: high geothermal gradient areas, which are regions with high geothermal gradients, such as Pannonian Basin, as I stated before, and low geothermal gradient areas, which in our case, it is the Carpathian Mountains, which have a lower geothermal gradient due to their geological structure. Now, low temperature resources is general available. That means with the usable drilling techniques, you may reach up to 30 degrees Celsius or 100 degrees Celsius. These low temperature resources are suitable for direct use applications such as heating, greenhouse heating, aquaculture, and balneoclimateric spas and resorts. Like we have one here close to Hunedoara, Gheoagiu, and which you may visit anytime when you travel in Romania. Now, medium temperature resources, this is the interesting part. These are a little bit limited than the use. So the temperature, it is between 100 Celsius to 150 degrees Celsius. Now, the application, as I stated before, it is district heating system, greenhouses, fish farming, and geothermal aqua parks. The transfer of the energy between the geothermal layer It can be done by using duplets. That means through two wells. And the exchange of energy, it is using a fluid environment, which gets in contact with the high temperature layer. We have the injection well and the production well, and also we may have a monitoring well. This energy heating, the liquid heated at the temperature of the underground, it is inserted in a heat exchanger, and depending on the cycle, that means the thermal cycle, we may have an ordinary Rankine cycle or a Kalina cycle. And we will discuss about these processes later. This is the diagram of primary and secondary circuit. We have the production well with valves, this and pumps, the steam mixture with water. It is introduced in a separator. The steam is used in a turbo alternator, and the output under the form of a mechanical energy, it is used by a generator. In the second cycle, we have a condenser and a cooling tower in order to recover the output energy, which can be used for heating and for greenhouses. Now, in this study, we have considered two cycles, ordinary Rankine cycle and the Kalina cycle. The organic Rankine cycle, it is a very simple one. Basically, we have a heat exchanger. The element used in this cycle, it is a liquid. And the transfer energy, it is sent to under the form of vapor to a turbine and produces energy. The Kalina cycle use different working fluids. Basically, it has a mixture of ammonia and as a main solution, and water, and it is rather a little bit more complicated, but it has a higher efficiency. Now, the Kalina cycle has a thermodynamic cycle used for converting energy into mechanical energy. It can use a lower temperature heat sources as geothermal, so it doesn't require higher temperature more than 100 or 200 degrees Celsius. The process structure, it is represented in this structure, in this diagram, where we can see the different loops for the working fluids. The efficiency of the system is represented in this chart. We can see the Carnot cycle, which has an overall efficiency or maximum efficiency of 25%. This is the ideal, and it is very hard or almost impossible to produce without special mixture of fluids and equipment. But lower than this, we have the Kalina cycle and the organic Rankine cycle. Now, the difference is that for 100 Celsius temperature, the Kalina cycle has a superior efficiency. What does it mean by this? We can extract more energy using an Kalina cycle rather than the organic Rankine cycle. That's why we have choose for evaluating the output of this application a Kalina cycle. Now, we present in this paper 3 studies. The output of the existing wells, it is estimated at 480 megawatt hour for a reference of temperature of 25 degrees. In this area, we have 96 wells which are operational, producing hot water in the temperature of 40 to 115 degrees Celsius, equivalent of 180 megawatt hour. In this area, we consider an improved technology. That means we can add to the Kalina cycle system also heat pumps, and we re-inject the water into the ground with a temperature of maximum 10 degrees. And this provides us with an average of 136 megawatt hour. Now, we consider the system for the process a cascade system. This value is calculated and evaluated using the formulas presented in this slide. And first application, it is considered the heating for 90 hectares of greenhouses in Romania. The efficiency of the solution, it is evaluated in the capability of the system to produce the necessary heat. And we can see that in this case, we have a good coverage. And we can see here the diagram of the process. Basically, we have a duplet, 2 wells, which are connected with pumps, and through a heat exchanger, the heat it is distributed between greenhouses and residential building. Also a cascade system where we have greenhouses and residential building. In this situation, the return thermal energy, it is used in the greenhouse. So we have a basic loop, and also we have heat pumps which can extract additional energy from the lower temperature return fluid. That means below the usable temperature. Now, here we have the amount of energy which is recovered from, extracted from the well. The estimation of the investment is around 20 million euros. The costs are evaluated using standard prices for the equipment. Now, the return is estimated to be around 21 months. This is due to the latest economical developments, since we have a rather increasing inflation in Romania for the food and for the energy prices. Also, the second application, it is related to a district heating system. The capability of the geothermal source is estimated to be able to support around 65,000 apartments and houses. Now, in this case, the investment is around 470,000 euro, and the return in time, or the investment recovery, is 23 months. The third application, it's a combination of those three, the two previous ones. We have a combination of greenhouses, fish farming, and power plants. That means we also produce energy, electrical energy, which is injected to the national grid. This is a really interesting solution, since we use the geothermal energy as a battery, and the price of the energy, it can be variable depending on the moment of the day when we inject energy. So with a careful automation solution, we may have a supportive element for the grid. That means we can inject energy to the grid when the solar and the wind resources are not available, since the heat is always available. And we can stop the production when the price is low. In this case, we can have a stabilization of the system, and it is a good application solution. Now, in this situation, the recovering period is 25 months. The investment is really large. It is almost 90 million euros. But with the global European, global or international support and European policy for the green resources, this can be covered easily through a support grant. Now, as a conclusion, in this paper, we presented a solution which is according to the European directive, starting with 2020, and it is mandatory, which states that it's mandatory that at least of the 20% of thermal energy used in the district heat